You type a question into ChatGPT, and man, it really feels like there's a mind on the other side, doesn't it? It feels like it's reasoning with you, thinking about your prompt, and genuinely understanding what you're saying. But what if I told you that under the hood, there might be absolutely zero thinking going on? Today, we're diving into one of the fiercest, most polarizing debates in modern science. It's a debate so intense that it actually prompted a billion-dollar bet from one of the founding fathers of AI regarding the entire future of the industry. So, are these systems secretly building complex, hidden maps of reality deep within their digital brains? Or are they literally just the world's most expensive parlor trick? Welcome to this explainer. Right now, top computer scientists are totally divided on this exact question. On one hand, you have researchers arguing that our current massive AI models are nothing more than mindless mimics, just aggressively stitching together words without any real grasp of what they're actually saying. But then, on the other hand, an emerging group of researchers is finding some pretty shocking empirical evidence that these models might secretly be constructing intricate internal models of the physical world. To figure out who's right, we first have to understand the trick behind the magic.
Okay, let's dive into this. Part 1, the engine. To get to the bottom of this debate, we really need to look under the hood. At their absolute core, modern large language models have a deceptively simple mathematical objective. It's called next token prediction. Think of it like a highly advanced autocomplete on steroids. Given an initial context of past tokens, which are basically just chunks of words, the network computes a conditional probability distribution over a massive dictionary to guess the most statistically plausible next word. Essentially, it's just playing a massive, high-speed game of fill-in-the-blank. This all runs on the famous transformer architecture, which was introduced back in a landmark 2017 paper called Attention is All You Need. Before this paper dropped, AI really struggled to remember context over long paragraphs because older models processed words sequentially, one by one. The transformer completely changed the game by introducing a mechanism called multi-head self-attention. This allowed the model to process entire sequences in parallel, calculating exactly how strongly every single word in a prompt relates to every other word, regardless of how far apart they are in the text. Let's walk through exactly how a prompt turns into a response, because it's pretty wild. First up is tokenization, where your text gets chopped up into standard numerical IDs. Next is the embedding projection. That's where those IDs are plotted out as dense vectors in a high-dimensional space, essentially grouping similar concepts near each other. Then comes the real magic, self-attention. The model creates query, key, and value matrices to weigh the importance of every token against all the others. Finally, the softmax projection takes all that incredibly complex math and spits out a simple probability distribution, ranking the most likely next words. It guesses the word, tacks it onto the sequence, and then starts that whole massive process over again.
Moving on to part 2, the parrot on the shoulder.
So knowing that it's all just math and probability, does the AI actually know what it's saying? Well, this brings us to a highly controversial 2021 paper by AI researchers including Emily M. Bender and Timnit Gebru. They introduced a devastatingly simple critique known as the stochastic parrot hypothesis. Now, the word stochastic basically means randomly determined or based on guesswork. Their argument is that these massive large language models are effectively just stochastic parrots. Just like a parrot mimicking human speech without actually understanding what the words mean, an AI is just haphazardly stitching together linguistic patterns it observed in its vast training data. Sure, it might sound incredibly smart, but there is zero actual comprehension happening. The absolutely crucial point here is the fundamental difference between form and meaning. These researchers argue that a system trained purely on the form of language, which is just static text files scraped from the internet, cannot, in principle, learn the actual meaning behind it. Think about it. Humans learn language by interacting with a physical environment, right? We touch a hot stove, we smell a flower, we share communicative intent with other people. An AI? It just sees billions of text strings. It has absolutely no physical grounding. Because the model is just a really confident word guesser. It has no internal concept of truth or falsehood, none. And this is exactly why you might have seen an AI confidently give you completely incorrect information. It just outputs whatever sounds statistically probable. This total lack of real-world grounding makes the model highly vulnerable to hallucinating facts, and it does so without ever knowing that what it's generating is actually wrong. Which brings us to part 3, the reversal curse. If the stochastic parrot theory is right, we should be able to trick the AI with some pretty basic logic puzzles. Let me ask you a question.
If I tell you that Olaf Scholz was the ninth Chancellor of Germany, and then a few minutes later I ask you, hey, who was the ninth Chancellor of Germany? You can logically deduce the answer is Olaf Scholz. Humans easily reverse facts. But autoregressive language models, they actually suffer from a massive failure of logical deduction here. Studies show that if an AI is trained on a sentence structured as A is B, it does not automatically generalize to the reverse direction of B is A.
In a fascinating study by Berglund and colleagues, they tested models like GPT-4 on real-world celebrity facts, and the contrast in the data is wild. When the model was asked, who is Tom Cruise's mother, it got it right 79% of the time, correctly identifying Mary Lee Pfeiffer. But when asked the reverse, who is Mary Lee Pfeiffer's son, the accuracy plummeted to just 33%. The model didn't actually learn the relational fact. It merely memorized the prevalent pattern in the exact order it usually appears in its training text. Again, it's mimicking, not thinking. But wait, there's more. Part 4, the Othello world model. So, case closed, right? The AI is just a giant parrot? Well, actually, scratch that. It's not quite that simple. Just when it seems AI is a mindless mimic, new empirical evidence suggests something breathtaking is happening deep inside those neural networks. Researcher Kenneth Lay and his team set up a brilliant experiment using the board game Othello. They trained a GPT model purely on sequential strings of text that represented legal Othello moves. Literally just strings of coordinates like E3, F4, C5. They didn't show the model a picture of a board. They didn't program any rules of the game into it. They just told it to predict the next text token in the sequence. The results were absolutely staggering. Despite only ever seeing text tokens, the model, which they dubbed Othello-GPT, learned to predict valid next moves with an error rate of less than 0.01%. But how on earth could it do that without knowing the rules? Was it literally just memorizing billions of text sequences? To find out, the researchers used probes to look inside the model's digital brain, and what they discovered is mind-blowing. The AI had spontaneously learned an emergent internal 3D map of the Othello world. Without any cross-modal supervision at all, the model figured out the complex spatial state of the board just by tracking the statistics of the text. Recent follow-up studies tested even more models and found they achieved up to 99% accuracy in unsupervised grounding. They aren't just predicting words anymore, they're actually modeling the underlying process that generates the data. Part 5, the search for meaning. So, we have models failing basic logic tests like the reversal curse on one hand and then spontaneously generating 3D maps of board games on the other. This brings us right to a philosophical frontier, and we have to revisit that core theoretical roadblock. Researchers Emily Bender and Alexander Kohler argue that, independent of passing a Turing test, these massive datasets might just be a mirage. If all you have is the form of language, you cannot learn meaning. Yes, the Othello experiment is incredible, but a chessboard is a closed, highly structured mathematical system. Does learning the rules of a board game actually translate to understanding the messy, physical reality of the human world? This is a classic dilemma in computer science known as the symbol grounding problem. It's often illustrated by John Searle's famous Chinese room thought experiment. Imagine a person locked in a room, given a massive rulebook to perfectly translate Chinese characters that they don't actually understand. To the outside world, they appear totally fluent, but inside, there is zero comprehension. Bender and Kohler use a very similar concept called the octopus test to prove that perfectly manipulating symbols, which is exactly what a language model does, is just not the same thing as connecting those utterances to the physical world. And this leaves us right at the edge of the unknown. We've seen that transformers are incredibly powerful prediction engines, perfectly capable of mapping complex hidden structures from sheer data. Yet, they still stumble on basic logical reversals and completely lack physical grounding. As these models scale to unprecedented, massive sizes, this is the billion-dollar question we all have to ponder. Can a machine trained purely on text ever truly bridge the gap to actual human comprehension? Or will language alone never be enough to truly understand reality? Thank you for joining me on this explainer. I really hope this helps you see the AI matrix just a little more clearly.